Yep.
Okay. Now, first of all, thank you very much for letting me give this talk. I really enjoy giving these talks at the Society. The background to this was Elizabeth and I and somebody else, my apologies, were at a talk at Sydney University. And after the talk, Elizabeth said, would you mind giving a talk on Nancy Roman? And I thought, oh yeah, don't know a lot about it at the moment, but more than happy to do it. So I've done a bit of research and put together the presentation. Because the presentation wasn't due to be given until July, August, or whatever, it's 95% done. So please excuse some of the wordsmithing, and I was going to move a couple of slides around, but nevertheless, here we go. Um, the Nancy Roman Space Telescope. Can you see the heading? I can't see the heading on my screen. Is that all okay?
Not chopping it off for me. I can see it.
Okay, great. Great. That's fine. That's fine. Okay, what I'm going to talk about today is, first of all, who was Nancy Roman and why did they name a telescope after her? The history of the project's objectives, some technical specs, and a bit of discussion on the instruments, and a little bit more detail on the key objectives. And this telescope really is going to push the boundaries a little bit. When I gave the talk on James Webb,
Mm.
um, the basic thesis of the talk is this telescope's going to really open our eyes and change the way we view the cosmos. Well, it certainly has, and Nancy Roman goes the next level. So that's a picture of Nancy Roman, the telescope, and I'm going to talk about this a little bit later on, but it might kind of look a little bit familiar. It's got some similarities to the Hubble telescope, and there's a good reason for that. The Hubble telescope was donated to NASA by the NRO, the intelligence agency in the United States. It was a surface spy satellite. And it was really the same with the Nancy Roman. It's a surface spy satellite that they gave to NASA, and they converted into this satellite. This this slide gives you an idea of the field of view of the telescope. That little square in the top left is what Hubble can see with each one of its photos, each one of its images that it takes. The large image is what Nancy Roman sees with each one of its images. So in one image, it can see many times more than what Hubble can see. And it's not just the increased field of view that sets this telescope apart. There's a few other things as well. So who was Nancy Roman? Well, these are some pictures of her. There are also some pictures of her later on in life, but they're not very positive pictures of her. She was active right up to almost her last days. But she was one of the top managers and astrophysicists within NASA. And you can see her in some of the roles that she was doing through her brilliant career. So, Nancy Roman, born in 1925, died in 2018. Her early life, she went to the University of Chicago. While she was a student there, she approached three professors. For a woman in that period, she was a very liberated, very forward woman, which is great. When she was there, she approached three professors to ask for work that she could do. And she was given from each of those professors a work on astrophysics theory, a work on data management, and an observation of a telescope type project to work on. And she did her PhD on the Ursa Major moving group in 1949. So just keep a bit of an eye on these dates, because we're talking about a long time ago when the knowledge of astronomy was very different to the knowledge we have today. She went to the is it Yerkes Observatory for 6 years as a research associate, and her work there resulted in some of the most highly cited papers of her time. So a young person, and she wrote some highly influential papers. She surveyed all the naked eye satellites and realized that they could be classified into two main groups based on chemical content and motion, which is something that other people had not thought of at the time. She realized that all stars are not the same. Remember, we're talking about the 1950s, very different scientific age. And her paper on the movement and location of stars in the Milky Way galaxy was selected as one of the 10 most important papers in 100 years by the Astrophysical Journal. She noted the spectral nature of stars varied over time. She published a catalogue of 600 stars in 1955. And she developed a method to find stars, which she called the UV excess method, and that method was used for decades afterwards. In 1959, she wrote a paper on detection of extraterrestrial planets using space-based observatories. Now, that was a very prescient discussion paper. She was 34 years old when she was talking about essentially the Hubble telescope in 1959. She worked for 3 years at the Naval Research Laboratory, becoming head of the microwave spectroscopy section. She consulted to Project Vanguard. She was concerned that the rockets, this is as a young person, she was concerned the rockets were not of a high quality. So this gives you an indication that not only was she smart and progressive, she also insisted on high quality in everything that she did. She pioneered the use of microwaves, and her theoretical work was then used to measure the distance to the moon in 1959 and hence the mass of the Earth. This is someone who's 34 years old. So just think back, what were you doing when you were 34 years old? Then she was invited to speak at the dedication of the Boyarkan Observatory in Russia. And she was the first civilian to visit Armenia to give a speech after the start of the Cold War. So she was very highly regarded at this young age. And this helped to build her international reputation. Her reputation was recognized by NASA, and at a lecture at NASA, she was approached about whether she knew anyone interested in creating a space astronomy group at NASA. That was, in essence, her job interview. And she began work at NASA in 1959. So she started as head of the Observatory Astronomy Unit at NASA. She was instrumental in converting ground-based observation framework to space-based strategy. And she was fighting entrenched views and egos. You can imagine a group of scientists who have an entrenched way of doing things. And she came along as a woman in those days, and changed the view of the men who were entrenched on how they should do their work. Again, that gives you an idea of the sort of person that she was. Also, she began the concept that the work at NASA should be available to benefit the broad global population. Through the 1960s and 70s, she was the sole authority for approving proposals for NASA's astronomy projects. From 1959, she led the Orbiting Astronomical Observatories program within NASA, and her team developed and launched the Orbiting Astronomical Observatory in 1968 and Copernicus in 1972. Her team designed several successful satellites, including X-ray and gamma-ray based. She designed several experiments on Spacelab, Gemini, Apollo, and Skylab. She set up NASA's scientific balloon program. She led the design of NASA's airborne astronomy program, including the Cooper Airborne Observatory in 1974. And she was also involved with a whole lot of other programs, including Hubble. NASA recommended that Hubble was to be controlled directly from Earth. Roman, again, being the thoughtful and progressive person that she was, stated this was ridiculous and led the design of autonomous space telescope control systems. Roman was responsible for appointing the engineers and scientists to design and build Hubble, and the program management processes that she established while designing and building Hubble are still used by NASA today. So that's who Nancy Roman was. Highly accomplished person, and she worked hard right until her last days. And she was designated the mother of Hubble. So she set up the Committee of Astronomers and Engineers in the 1960s that envisaged how in-space telescopes could revolutionize scientific research, and these efforts began the path to the Hubble Space Telescope. So you can see why NASA wanted to honor her with the name of a space telescope, one of the most recognized people within the NASA community. So talking about the telescope itself, it was recommended in 2010 by the US National Research Council, the Decadal Survey Committee, which meets and reports once a decade. And in 2010, Nancy Roman was determined to be a top priority project for NASA and the US government. It was approved in 2016, and at that time was moved from a study status to project status. And the estimated cost at around that time was US $2 billion. In 2017, unfortunately, NASA was told to reduce the cost of the project by Congress when they were approving the budget. And the cost in 2020 rose to between 3.2 and 3.9 billion, which included, 5 years of operation. So roughly $4 billion for 5 years of operation. The Decadal Survey rated this telescope as the highest space mission priority for the 2020s. We're in 2024 at the moment, so that tells you something. But then in 2018, Congress approved more than NASA had requested for this telescope, and also rejected the cancellation of scientific programs. So Congress had changed its view of this telescope and recognized the importance of the Nancy Roman telescope. It was named after Nancy Roman in 2020, and it was originally scheduled to launch in October 2026, and I believe the current launch date is May 2027, plus or minus a month. So this telescope was originally called WFIRST, the Wide Field Infrared Survey Telescope, and renamed, as I said. It's a 1.3 meter diameter mirror, only one instrument, only one mirror in the telescope, but there are two bits of equipment hanging off that one mirror. In 2012, the NRO, as I said at the start of this talk, the NRO, SPIES, offered to donate 2 telescopes, the same size as Hubble, to NASA. Remember from my previous talk on Hubble, Hubble itself was a SPIES telescope that was surplus to needs. There were several locations to put this telescope. One was in geosynchronous orbit around the Earth, and the other one was at the Earth-Sun L2 point, Lagrange point 2. And don't forget that L2 is where James Webb is at the moment. There are various advantages and disadvantages of Lagrange point 2. The advantages are improved observation capabilities. It doesn't have to worry about stray emissions coming from Earth. There's better thermal stability, and you might remember they took several months to cool down James Webb before they put it into full use, because they had to get it cold and they had to keep the equipment thermally stable. And there's a more benign radiation environment out there. The disadvantages of L2 are, first of all, the inability to repair the satellite using current technology. However, Nancy Roman, like James Webb, does have grabs on it, so that if they ever do develop a robot to repair it, the robot can grab the telescope while it's doing repairs. Extra propellant obviously is needed to get there, so you need a larger rocket to get it off planet Earth. There's a lower data transfer rate from Lagrange point 2 to Earth, but as I'll say in a few minutes, that's not a big problem for Nancy Roman. And also the time delay for commands and communications. So the telescope needs to have a modicum of automation, so that it's not relying all the time on direct commands from planet Earth. Okay, the project objectives. What is this telescope going to do? The Nancy Roman Space Telescope will be cutting-edge space telescope for in-depth studies of the universe in infrared light. The telescope's large field of view, high sensitivity, and advanced coronagraphic capabilities will allow astronomers to detect and study galaxies in the very early universe, search for potentially habitable exoplanets, non-Earth planets, and provide answers to some of the most pressing questions in astrophysics, such as the nature of dark energy and dark matter. The telescope, as I said, is an infrared space telescope. The two instruments are the Wide Field Instrument, which is a 300 megapixel multi-band visible light and infrared camera, and the Coronagraphic Instrument, which is the high contrast small field of view camera that will also operate in the visible and near infrared. And it includes some new starlight suppression technology so that it can observe planets orbiting stars directly. And it has a resolution of 0.15 arc seconds from planet to the host star. So that's a resolution of the photos, the images it'll be able to take. The Coronagraphic Instrument is also specifically designed to test new technologies for inclusion in the next generation space telescopes, telescopes after Nancy Roman. So Nancy Roman will also be a test bed, if you like, for the next generation space telescopes. The instrument will be able to see planets orbiting stars that are 1 billion times fainter than the host star. It blocks out the host star light by creating an opposite light wave that works in the same way as noise-cancelling headphones, and hence removing the light signal from the host star. Most coronagraphs, as we know, simply put a disk in front of the star to crudely remove the star's light. This device will electronically create an image the opposite of the star, and hence the image of the star plus the opposite will cancel the star out. And that's shown in this diagram here. The top sinusoidal wave is light coming from the star. The second sinusoidal wave is the cancelling frequency, which is generated by the telescope. And the net result is no star. And that's very similar in concept to the noise-cancelling headphones that you might wear yourself. And as I said, the Nancy Roman, like space telescopes before it, is blazing a technology path for future missions. So it's also a test bed for the next telescope to come. There are several project partners, the French Space Agency, the European Space Agency, and the European Space Agency is involved in a number of NASA projects, either directly or indirectly, the Japan Aerospace Exploration Agency, and the Max Planck Institute. So this is, I was going to say, a global project. Of the Western world, is pretty much a global project. Also, there's ground support at the White Sands. It's a NASA facility, Misada Station, which is a Japanese facility, and New Norcia Station in Australia. And when I read that, I went, what? Where is New Norcia? So this is an ESA, a European Space Agency Earth Station, built in Australia for communication with spacecraft after launch in low Earth orbit, geostationary orbit, and in deep space. It's located 10 kilometres south of the town of New Norcia in Western Australia, and it was the first European deep space ground station, and there's a couple more now. Now, it's not very helpful to say 10 kilometers south of New Norcia, because your first question is going to be, where on earth is New Norcia? So I've got a map down the bottom left here. You can see Perth, and the ground station is the red marker north of Perth. So that gives you an idea of where it's located. And the photo on the right is the ground station, New Norcia. As we always do in these sorts of talks and presentations, comparison of this telescope to the ones that we know, Hubble and James Webb. I've got a diagram that shows you the wavelength coverage. It's in an easier form than this table. And the mirror is the same as Hubble, 2.4 meters, but far smaller than the multi-panel James Webb mirror, which is 6.5 meters. Now, it's not the size of the mirror that's important here, it's what you do with it. And I'll come up with that some discussion on that later on. Okay, so I said before that one of the tasks of this telescope is to give us a little bit more information on what dark matter and dark energy are. So why is that important to understand? Well, as most of us know, the matter that we talk about, the galaxies, planets, gases, meteors, everything else, that's, as far as scientists are currently aware, about 5% of the universe. So what the scientists are saying is we've got all these great equations and theories and pictures, but that's really only 5% of what's out there. We need to understand what the other 95% is. Now, this telescope is not going to tell us what the other 95% is, but it'll give us some information on how this stuff, the dark matter and dark energy, interacts with galaxies. And that, when you build a very large statistical database of thousands of galaxies and thousands of movement types, you get a bit of an understanding of the distribution of dark matter and dark energy in a way, and hence you limit what these entities may be. So that's the idea. I said here that Nancy Roman may actually detect the first traces of dark energy by analysing an unprecedented number of galaxies and their clustering and distribution characteristics, hence inferring indirectly some of the characteristics of dark energy. So we're not going to snap a photo of it. We're going to observe how things are moving around the universe and infer some relationships from those movements and locations. This telescope has a nominal 5-year mission duration, but there is the potential to extend this out to 10 years. And that depends on a couple of things. It depends on fuel use, and James Webb taught us a lot about how to get to L2 with conserving fuel. And if we conserve fuel, then we extend the life of this project. Another thing that could limit the life of this telescope is a meteor strike. Now, James Webb has been hit by a couple of particles of dust already that have caused a little bit of damage, not much. It doesn't take much of a meteor to cause a fair bit of damage to a telescope sitting out at L2. Also depends on the software reliability. Now, I don't have a personal problem with that because NASA has shown us that it can write some very, very robust software. And this telescope is expected to gather and transmit 20 petabytes of data over 5 years. So we go, what is a petabyte? I know what a gigabyte is. What is a petabyte? Well, a petabyte is, you can see it down there, it's 1,000 terabytes, it's 1,000,000 gigabytes. So it's a lot of information, and there's a slide coming up, which I don't think's the next slide, but it'll show you the data being returned by this satellite compared to Hubble. In 5 years, this telescope will gather 30 times as much data as Hubble has in its lifetime. 30 times as much in 5 years. So if it goes for 10 years, which I think it just might, that'll give you 60 times as much information as Hubble has already. So what are the some of the other objectives for this satellite, this telescope. I mentioned briefly before searching for extrasolar planets using gravitational micro lensing, analysing the chronology of the cosmos, so look back deep in time and look at how the cosmos, how the universe has changed over its life, analyse the growth of cosmic structures, measuring dark energy, analysing general relativity, where does it break down or not, and also analyse the curvature of space-time. And I was reading today yet another theory on does dark matter actually exist. One of the theories that they're trying to put forward, some people are trying to put forward at the moment, is that the space-time continuum has a bit of a wobble in it. So if there is a bit of a wobble in it, then analysing the curvature of space-time can either validate or not validate that theory. So when this telescope looks for the evidence for dark energy, it's not going to look for dark energy, it's looking for the evidence of dark energy. This is a very complementary mission to the ESA Euclid mission. And one of the things that scientists want to determine is the acceleration, should be cosmic expansion, caused by a new energy component being dark energy, or by the breakdown of general relativity on cosmological scales. That's to say, is the energy density constant in space and over time? Because this will help us understand what that 95% of the universe really is. We won't actually be able to see it, but it'll give us some indirect observations of what dark energy is doing to the universe. One of the other key things for the satellite is a census of exoplanets. And one of the reasons we're interested in that is because we are intently looking for signs of life out there in the universe. So this telescope will study the number, location, and nature of exoplanets. Now, the location, of course, is relevant to the Goldilocks zone around stars. Are the planets we find potentially habitable for life? The instrument sensitivity. This telescope will be able to locate exoplanets with a size down to a mass only a few times that of the moon by gravitational microlensing. And I've got a little diagram showing you microlensing in a sec. It will also be able to locate and count free-floating exoplanets down to the mass of Mars. So that is Mars-sized bodies that are drifting between the stars. And in its life, this telescope is expected to measure the transits of 100,000 planets to a distance from Earth of 10,000 parsecs. Now, to give you an idea of how big that is, the Milky Way galaxy diameter is 30,000 parsecs. So this telescope will be able to measure transits of planets across the host star to a significant portion of the Milky Way galaxy. Also, it'll have a bit of a look at the solar system itself, and it'll be able to detect long period comets. We struggle with that at the moment because we don't have the resolution, but this telescope will have the resolution to help us detect long period comets. Detect some 5,000 trans-Neptune objects. Detect small objects, 20 to 2,000 kilometer diameter in the inner Oort cloud. So that's a distance of 100 to 800 astronomical units, 100 to 800 times the distance of the Earth from the Sun. So we're looking at finding objects that are 20 kilometers diameter at that distance, essentially from us. And also do some spectroscopy work as well on the planet's surfaces, so that we get an indication of what chemicals are on these planets. Again, looking for the probability of primitive life on other planets. Okay, microlensing. We know what basically a gravitational lens is. It's when a star moves in front of the image of either another large star close by or a galaxy. And with that lensing, we can do all sorts of things with the closer star that we couldn't do if the image wasn't distorted and magnified by the gravitational effect. With microlensing, we can do the same thing with planets. As a planet moves around its host star. So the apparent shape of distant galaxies gets warped by clumps of dark matter between the telescope and the galaxy. By studying the extent and nature of this warping for a large number of galaxies, Nancy Roman will give some clues as to the distribution and physical nature of dark matter, also using the same technology for planets. So here's a diagram that I found of using microlensing to detect planets. So as an object moves in front of a star, a light-emitting object further away, we know the lensing effect that we get. This telescope will have a resolution such that if there's a planet orbiting that star, it'll also pick up the lensing effect on that planet, not only on the star. Dark energy. By mapping the location of many galaxies and clusters of galaxies, this telescope will provide more detailed information on the expansion of the universe and the acceleration of this expansion. Its wide field of view allows Nancy Roman to observe many galaxies in a short period of time. By indirectly studying dark energy, Nancy Roman will add data to the debate on whether the acceleration of the universe's expansion is really due to dark energy or due to a breakdown of the general theory of relativity at large distances, or indeed just in certain locations in the universe. Just because the physicists like to say that the rules of physics are uniform throughout the universe, doesn't necessarily mean that's the case, although you'd expect to see some distortions at the intersection of two different physical constants. But it's a possibility, so let's not rule that out. The Roman telescope will be able to scan regions of space 1,000 times faster than Hubble can today. And as I said before, Nancy Roman is designed to complement both Hubble and the James Webb and integrate with next-generation ground-based facilities such as the Rubin Observatory Telescope. So whenever we talk about whether it's Hubble or James Webb or Nancy Roman or any of these telescopes, they really are not just one telescope. They are a group of telescopes that are working together, and where their missions are aligned, it's not always the case. They're doing their best using the different technologies each one has to work out some of the key answers to some of the key questions we have in cosmology. It's a group effort. The wide field of view instrument will provide Hubble-style resolution over a field of view 200 times greater than Hubble's infrared field of view at the moment, while the coronagraph instrument will be capable of suppressing starlight by nearly 1 billion to 1. Now, the technology that's up in space at the moment can suppress starlight by a ratio of 1 million to 1. Nancy Roman will be 1,000 times better than that at 1 billion to 1. And the next mission, once Nancy Roman has proved up the technology, will be a 10 billion to 1 suppression of starlight. So that gives you an indication of the new sorts of information that we'll be able to get from this telescope. I've already mentioned this before. The amount of data that we get will help to redefine how we understand the cosmos. If what you're reading in the scientific press about James Webb intrigues you and amazes you, Nancy Roman is the next step forward. So this telescope is expected to image and study planets by the thousands, galaxies by the millions, and stars by the billions, and also question our current thoughts on cosmology and fundamental physics, and also test the limits of what we know. I've talked about that already. About 70, this is something important, and this is part of the legacy of Nancy Roman herself. Remember I said that one of the key things that Nancy Roman did was opened up NASA to be a public database. Well, 75% of Nancy Roman's the nominal 5-year mission will be devoted to core community surveys. So a lot of the time of this telescope won't be pre-scheduled per se, but will be open to scientists basically tendering, bidding for their projects on this telescope. Now, the High Latitude Wide Area Survey, this will be able to image 2,000 square degrees of observable space using a device called a GRISM. And what is a GRISM? It's a grating prism. It's a combination of a prism and a grating arranged so that light at a chosen wavelength passes straight through. The advantage of this arrangement is that one camera can be used for, let's call it normal imaging, and also by sliding in the GRISM, it can be used for spectroscopy work as well. So there's a diagram here that just shows if you only have a grating on the telescope, you get a fairly stock standard image. But if you put a GRISM on, then you can split the wavelength into different wavelengths and simultaneously take not 3 pictures, numerous pictures within that field of view. So you get a lot more data, a lot quicker, and you can analyze objects in different spectrums very quickly. Okay. So the High Latitude Time Domain Survey, another project with this telescope. Surveys will be taken every 5 days to observe supernovae with a Z-score of 1.7. Now, what is a Z-score? There's a chart here that shows a Z-score and age of that object, basically redshift. A Z number, a Z-score of 1.7 is equivalent to objects that are about 10 billion light years away, so formed about 3 billion years or so after the start of the Big Bang. So this telescope is going to take a lot of surveys every 5 days of the universe at an age of about, let's say, 3.8 billion years. I've gone through most of this. The Galactic Bulge Time Domain Survey, this is another project. We'll take an image every 15 minutes of a 2.2 square degree region of the Milky Way bulge to survey the characteristics of the center of our galaxy. So this will go every 15 minutes for either 5 years or 10 years. So there'll be a census of the exoplanets, the stellar population survey of our galaxy, and the structure of our galaxy. Now, don't forget, we really don't know a great deal about the structure of our galaxy. We know it's a spiral galaxy, and we know that there are stars and gas and dust through those spirals. But even today, before this telescope goes up, we're finding significant new information about the structure of our galaxy, because a lot of our galaxy really can't see very well. The dust really makes a mess of photos that we take. Okay, so infrared can see through that, with the work of our infrared imaging, we are getting today a great deal of new information on the structure of our galaxy. And again, Nancy Roman will take it to the next level. Now, this is, I've mentioned this before, but it's very, very important. None of these telescopes that I've mentioned sit on their own. They're all technical progressions of the previous telescope. So Nancy Roman will pave the way for future large space based missions. And that was discussed in the 2020 Decadal Survey. And one of the missions for Nancy Roman is to help scientists design instruments to directly image Earth-like exoplanets. So Nancy Roman will provide validation of current theories from its observations, data to question our understanding of the universe, data to uncover new theories of the universe, leads for future research, space telescope technology validation from its use on Nancy Roman, and hence pathways to new space telescope technology. I inserted this diagram because this shows the progression of satellites, telescopes, over the last couple of years. The top band of telescopes is the US, the NASA band of telescopes, and the telescopes underneath are the ESA telescopes. So you can see there a progression. You've got Hubble, you've got Spitzer, Kepler, TESS, James Webb, and then Nancy Roman at the end. It's part of a progression of technology and capabilities. And then, of course, the progression will keep on going after Nancy Roman. I think I've covered most of this slide. Okay, so the Planet Survey, it'll be able to detect via microlensing objects as small as 0.025 times the mass of the Earth. So that's like the mass of Ganymede. We're talking about small objects on this scale. Nancy Roman is expected to identify 1,400 planets with a mass greater than 0.1 times the mass of the Earth, and to calculate the mass and distance to each of these identified planets. So a very large, we have a lot of planets identified at the moment, but this will now identify smaller planets, not Jupiter-sized planets anymore. We're talking about planets the size of Earth, Mars, and smaller, depending on the distance, of course. Further away these objects are, the larger they have to be identified. With regards to the dark matter, the location of the dark matter effects, remember we won't see dark matter, but we'll see the effects of dark matter. The location of dark matter effects on the galaxies will help to determine whether dark matter is heavy particles, i.e. found in the early universe, or developed over a long period of time. Is dark matter something that's evolving over time? And that would indicate that today dark matter is lighter particles than if it was formed at the start of the universe. Now, that's what you get from the scientific literature. I would probably add to that if you do have a thing like the Big Bang, I doubt that it was a uniform event, explosion or whatever event. So you could probably have areas within the early universe of different sorts of particles. So I don't think the progression is as simple and as smooth as the scientific paper suggests at the moment. There may well have been a mixture of events at the time of the Big Bang because of the forces that were involved. I think I've covered most of this, just looking at what stars will be observed and the benefit of that. There'll be better analysis of galaxy interactions than we have at the moment, and more detailed analysis of black holes. Now, I mentioned before that this telescope won't operate on its own. It will operate in conjunction with several other telescopes that are either in space or located on planet Earth. And also we'll be able to combine data with the Reumann, Euclid and eROSITA telescopes as well. So this is really part of a global effort here. Now, Nancy Roman will generate a lot of data. Vast amounts of data from the telescope means new strategies to analyse the data have been developed ahead of the launch of Nancy Roman. The simulation and data analysis software is currently being written and tested by NASA. Also, the incorporation of machine learning, quote AI, to more efficiently and comprehensively identify data of interest within the masses of data that are going to come back, plus accelerated scientist collaboration encouragement. So it's one thing to get a lot of data back from the telescope. It's another thing to actually be able to extract out useful information from that data. I've got here just an expanded view of the guts of the telescope, taking the lining off, if you like. So on the top left here, we have the actual telescope itself and the two bolted on devices, instruments that I talked about, the coronagraph on the left there and the wide field instrument on the right. Now the other images here are just various stages of putting the telescope back together again and how the pieces fit together. But for our talk tonight, it's the top left diagram that's most significant. So that's the guts of the telescope. This image, it's a really good one because it shows what the Nancy Roman telescope can see at a time, which is that large grey outline, compared to Hubble, which is sort of centre middle, and the James Webb, which is also centre middle of this diagram. So Nancy Roman will see a lot more than either of those two other telescopes at a time. Now, there's a bit of a trade-off on that. James Webb can see deeper into space, but Nancy Roman can also see fairly deep into space, but with a very large wide field of view. And down the bottom, the wavelength diagram, if you look under the coloured part, you can see the spectrum that Hubble operates in. James Webb and the Nancy Roman telescope is sort of the binding glue, if you like, between those two telescopes as far as wavelengths is concerned. So Nancy Roman is the visible light and a small part of infrared. This image just shows the benefit of having a wide field of view. You can contextualize images. So rather than just saying, I found this great galaxy which is 5 billion years old, you can say, I found this great galaxy and this is its relationship to 100 other galaxies. And it's that relationship which is also very, very important. And this is a similar concept, looking deep rather than broad, if you like. So this is looking deep into space, to the early universe. As I said, James Webb can look deeper, further back in time, but Nancy Roman will look a fair way back in time. And again, it can contextualize rather than just saying, I found a really great galaxy formed 300 million years after the Big Bang, which is what we apparently can see from James Webb. Now we'll be able to say, I can see 100 galaxies that were formed 300 million years after the Big Bang. And this is their relationship to each other, the speed that they're going and what direction they're headed. So that is contextualizing a large amount of information, which you could do with James Webb, but it'll take an awful lot longer because you've got to take a lot more photos, a lot more images. Okay, and this slide puts the amount of data that we're going to get from Nancy Roman into context. The 172 terabytes, that little blue box at the top right, is the sum total of everything that we've got back from Hubble since the day we turned Hubble on. All of those blue boxes, 20,000 terabytes, is what we expect to get from Nancy Roman in 5 years. So one small box in 30 years, lots of blue boxes, 20,000 terabytes in 5 years. So that gives you an indication of not only what Nancy Roman will be able to do, but the advance in technology since Hubble, and also gives you an idea of how difficult it's going to be to extract the useful information, which is why NASA is working so hard at the moment on building the machine learning systems to extract the useful information out of all this data. Okay, so look, that was the end of the talk. There's a lot of really good websites that are available. I've got here the one of the official NASA Nancy Roman sites if you want to get some more facts on Nancy Roman. I think this is going to be a really exciting telescope, assuming it gets to L2 successfully. If you thought James Webb opened our eyes and asked more questions than it answered, wait until you get to Nancy Roman. Thank you very much.